In this video, we will learn about vector-valued functions and space curves. So, a vector-valued function is a function whose domain is the set or a subset of real numbers and whose range is a set of vectors. So these could be two-dimensional vectors or three-dimensional vectors, depending on the purpose that we are using the vector function for. And this is a nice way to connect single variable functions that we've studied in previous math courses with a function that now can output a vector that brings us into either 2 or 3 space. And you can go into higher dimensions if necessary, but in this course we're going to stick predominantly with vector functions in 2 and 3 space. As far as notation goes, r of t is equal to vector bracket f of t, g of t, h of t, or if we write it as a linear combination of I, j, and k, that would be f of t I plus g of t j plus h of t k. The functions f of t, g of t, and h of t are real-valued functions called component functions of r of t. And these are single variable functions. So all of the properties of single variable functions that we learned previously, whether it be calculus of single variable functions or domain and range, all of those properties will come through with vector-valued functions. And speaking of which, find the domain of r of t being equal to 2t over t minus 5, square root of 2t minus 1, natural log of 3t. So here, we need to find the domain of each component function and then put them together to create the most restrictive domain possible for the vector function r of t. So looking at our first component function, the domain would be t minus 5 cannot be equal to 0, so t cannot be equal to 5. The second component function, the domain 2t minus 1 has to be greater than or equal to 0, so t is greater than or equal to 1/2. And then the final component function, natural log, the input has to be greater than 0, so 3t has to be greater than 0, t has to be greater than 0. And now we put these 3 individual domain restrictions for each component function together to create the domain for r of t. So the domain t greater than or equal to 1/2 is more restrictive than t greater than 0. So we can focus on that. And then t cannot be equal to 5, which is part of being greater than or equal to 1/2. So using interval notation, our domain would be 1/2 to 5 and 5 to infinity. If we needed to, we could write t greater than or equal to 1/2 and t not equal to 5. That would be sufficient, but it is much nicer to write it in interval notation, in my opinion. Continuing, looking at vector functions and all of those pieces, the limit of a vector function, r of t, is defined by taking the limit of each component function. So if we remember how to take all of our limits in single variable calculus, that will carry through as we take the limit of each component function individually. So if r of t is the vector function f of t, g of t, h of t, then the limit as t approaches a of r of t is the limit as t approaches a of f of t, and the limit as t approaches a of g of t, and the limit as t approaches a of h of t. Okay, so we take the limit of each individual component function. Now that's provided the limits of every component function exists. If at least one limit does not exist, we'll abbreviate D and E, and that includes a limit that goes to positive or negative infinity, then we would say that the limit of r of t also does not exist. Okay, so suppose we were taking the limit as t approaches a of g of t, and we got a limit that does not exist, well then we can say that the limit as t approaches a of r of t does not exist. A vector function r of t is continuous at a if the limit as t approaches a of r of t is equal to R of A. Okay, so same definition of continuity from single variable calculus applied now to a vector function, which says the limit as we approach a point has to be equal to the vector function evaluated at the point. And that would be the definition of continuity. And if you see the note below, any of the techniques, so you can factor and simplify, rationalize, use L'Hopital's rule, any memorized limits. So all of those techniques that you built in single variable calculus to evaluate a limit will now be important to bring through as we evaluate limits of vector functions. Okay, so two examples. We'll take one limit as we approach 0 and one limit as we approach infinity. So limit as t approaches 0 of e to the t squared minus 2t over t, and sine t over t. Okay, so our first strategy is always to try to plug in the value that we're taking the limit of or approaching in our limit. So e to the 0 is 1. And then if we plug in to our second component function, we would have 0 over 0. So we need to rely on one of our techniques to evaluate this limit. So if I look at the numerator, I can take out a factor of t, which then simplifies with the factor of t in the denominator, and we're left with t minus 2. Reevaluating that limit would give us negative 2. And then sine t over t, as t approaches 0, is traditionally a memorized limit. It's memorized to be 1. But if you forgot that memorized limit because it has been a little bit of time since you've seen it, we can always rely on L'Hopital's rule here, because we would have 0 over 0. So we could take the derivative of the numerator and the derivative of the denominator, so cosine t over 1, and reevaluate the limit, and we would get cosine of 0 being 1. Right? So just a reminder, that's L'Hopital's. Now looking at the limit as t approaches infinity, so we're looking at end behavior of each component function. So first we have cosine t over t. So the cosine function has a range from -1 to 1, and the denominator being t, that means it will continue to increase. So as the numerator varies between -1 and 1, the denominator continues to grow, so that function will approach 0. And our second component function, e to the negative t, we can rewrite as 1 over e to the t. As t goes to infinity, e to the t will continue to grow, but since that's in the denominator of our function, this function will also approach 0. And then the third component, we have a rational function, 5t squared plus 2 over 3t squared plus t. So evaluating the end behavior of a rational function, we typically look at the highest degree in both the numerator and the denominator. In this case, they are equal. So if we simplified what's in the rectangle, the limit would be 5 over 3. Your other option there is to do L'Hopital's again, because you would have infinity over infinity, take the first derivative, and then in this case you would actually have to take the second derivative as well, so applying L'Hopital's twice in order to get the limit of 5/3. Okay, so we talked about the domain of vector functions, we evaluated a few limits. Now let's talk about graphing. The set C of all points x, y, z in space, where x equals f of t, y equals g of t, and z equals h of t, and t varies throughout the interval I, and where f, g, and h are continuous real-valued functions, is called a space curve. So, the graph of a vector function we call a space curve. As far as this definition is concerned, the important part here is that we are going to think about graphing a vector function the same way we graphed parametric equations in calculus. So we're going to think of the x value to be the component f of t, y will be g of t, and z will be h of t. And then the interval, if they tell us a domain, we'd only graph on the domain. If not, we would generalize the graph. And if you look below, there is an example of a space curve in 3-space. Okay, so we are able to define some pretty unique movement in 3-space with vector functions that we might not have been able to express with just a single variable function. Consider the curve C shown below. R of t equals 2t plus 4, t plus 6. Okay, so we have the graph, although it's not a complete graph. There's more information that we're going to need to include, but this is a good start. So the graph of this vector function is a line. So they asked to sketch multiple direction vectors. So for instance, r of 0, that would be 4, 6. And r of 1 would be 6, 7. r of 2 would be 8, 8. And since they don't restrict t, let's plug in one or two negative values. So we'd have r of negative 1 being 2, 5, and r of negative 2 would be 0, 4. Okay, so sketching these, I will use the arrow tool so the vectors look nice. So r of 0, so we'll start at the origin, and we go 4, 6. And what you'll notice, starting at the origin and going 4, 6, we wind up at a point on the line. And then r of 1, 6, 7. So 6, 7, similar result. Let's see if I can move that arrowhead just a little bit better. There we go. Okay, and then r of 2, 8, 8. And we end at a point on the line again. The negatives, 2, 5. So 2, 5. There's r of negative 1. And then r of negative 2. So essentially, the way we create a space curve is we take the terminal point of a whole bunch of vectors and we connect them to create our space curve, right? So this was r of 0, r of 1, r of 2, r of negative 1, r of negative 2. Okay, so all of those terminal points we got from each vector defined one point on the line. Now, this is helpful because the piece of information that we're missing on the graph of this space curve is to indicate the direction of increasing t. So in this example, if we look at our direction vectors, they indicate that the increasing t, or the direction of increasing t, goes from left to right. So we have to indicate that, right? So in the graph of our space curve, we not only have to show the x and the y, the terminal points of each vector, but we have to include information showing how t is changing as well, right? So this is the way that we'll represent those three variables, x, y, and t, in the graph of a space curve. Graph the curve C defined by r of t equals cosine t sine t, and be sure to indicate the direction of increasing t. Okay, so essentially we want to find a few vectors to define the points on the space curve, and then we'll use those vectors to also indicate the direction of increasing t. So I find it helpful to create a table, and now our table will have a t column, an x column, and a y column. And the xy, that's like a vector, right? x, y, output. So t being cos t sine t, so let's go 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so then x would be 1 and y would be 0 at t equals 0. And then we have 0, 1 at pi over 2, negative 1, 0 at pi, 0, negative 1, and then back to 1, 0. So we do have a large graph here. So instead of just using one box as 1, let's open it up a little bit to give ourselves some space. So I'll go every 4 just to use a few more boxes in our graph. So that's 1, negative 1, and negative 1. Right, so we don't need to draw in the full vector every time. We're most concerned with just the terminal point. Right, so t equals 0, you'd have the vector 1, 0, so origin out to 1, 0. So we can just make a point at that terminal, the terminal point of the vector. And then 0, 1, negative 1, 0, 0, negative 1. Okay, so hopefully we can pick up that it would be circular, even just from those 4 points, knowing cos t sine t, how that behavior works. Okay, so I'll try to draw the best circle that I can. And then we also have to indicate the direction of increasing t. So in this case, we are moving in the counterclockwise direction, right? This was 0, pi over 2, pi, so on and so forth. So So then the follow-up question is, what would change if the vector function was changed to r of t equals sine t cos t? So we're still using sine t and cos t to define the component functions, but we switched which component function was sine and cosine. So let's just make a table of values, and we don't need a full table of values so that we can compare. So let's just go 0, pi over 2 pi. And if that's not sufficient, we can always expand our table. So at 0, we'd have 0, 1. And then at pi over 2, we'd have 1, 0. And then at pi, we'd have 0, negative 1. So it will define the same set of points, but the direction will be different. So we'd start at 0, 1, then go to 1, 0, then go to 0, negative 1. Right? So the direction of travel, the direction of increasing t, would be clockwise in that instance, not counterclockwise. Now, this is important just to pick up on because there will be certain examples where we have to move in a certain direction, so the way the vector function is defined will matter. In other cases, we're just trying to generally define a space curve in either direction, and we have a little bit more freedom in those examples. Now let's move into 3 space. So graph the curve C defined by r of t being cos t sine t on the domain t is greater than or equal to 0. Be sure to indicate the direction of increasing t. So same start, let's make a table. So t, now this table will have more columns because we need an x, a y, and a z. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we plug in, so we'd have 1, 0, 0. 0, 1, pi over 2, negative 1, 0, pi. 0, negative 1, 3 pi over 2, and 1, 0, 2 pi. And now let's plot these points as best we can. So we have x, y, z axes. So 1, 1. We need to go negative 1, so I'll extend both axes. And I'll break the z axes down. Pi over 2 pi, 3 pi over 2, and 2 pi. Okay, so we plot our points. So 1, 0, 0. 0, 1 pi over 2. Negative 1, 0 pi will be back there. 0, negative 1, 3 pi over 2 will be up here. And then 1, 0, 2 pi. I'm going to wait to plot that point until we sketch, just so my perspective can be correct. So we start here, and then we're going to go through the points in a circular motion as we continue to go up along the z-axis. Okay, so it's going to be a helix curve around the z-axis. There's your direction of increasing t. Now that point 1, 0, 2 pi, that's going to be over 1, even with 2 pi, so that's like there on our graph. Again, perspective's a little challenging, trying to graph 3 dimensions on 2-dimensional piece of paper, okay, but we have a general idea of what it looks like. Now, in this case, they asked, would the graph of the vector function r of t being sine t cos t be the same? So again, they switched the sine and the cosine. But in this case, because we have the third dimension, we need to be a little bit more careful. So if we made a table of values again, and again, we don't need too many of them. So let's just say 0, pi over 2, and pi. So now at 0, we'd have 0, 1, 0. At pi over 2, it's 1, 0, pi over 2. And then at pi, it would be 0, negative 1, pi. So if you think about where those points would be plotted, it would be a totally different curve. Still a helix, but the points wouldn't be the same. Right? So the simple answer here, would the graph be the same? No. So in that last example in 2 space, both of those vector functions wound up defining the same set of points, just in different directions. And now in 3 space, that slight change gave us a completely different graph. Right? So one of the challenges with moving into a third dimension. The last thing we have to talk about is creating our own vector functions. So we can use parametric equations to create a vector function that represents a given curve. And this is going to be important throughout this course, being able to define a curve as a vector function, because then it allows us a whole different set of operations to utilize. So one strategy is to set the independent variable equal to the parameter t. So here, find a vector function that defines the graph of y equals x squared from the point -1, 1, 2, 3, 9. So y equals x squared, x would be the independent variable. So put simply, x would be t. And then based off of that, y would be t squared. So our vector function, r of t, would be t squared. And then to define it from the point -1, 1, 2, 3, 9, since we define x to be t, then t goes from -1 to 3. And we include that domain restriction. Right? And talking about the different tools that this opens up, if we were to integrate this vector function, then this interval would provide us with bounds of integration. Now stepping that same idea up into 3 space, find a vector function that represents the curve of intersection of the plane y plus z equals 1 and parabolic cylinder x equals y squared. So we can define both of these surfaces in terms of y. Z can be 1 minus y, and x is y squared. So building out from there, we'll call y t. Then that means x would be t squared, and z would be 1 minus t. So our vector function, r of t, is t squared t 1 minus t. And we've defined the curve of intersection. Okay, so that's our first strategy. Next, making use of Pythagorean identities. In particular, cos squared t plus sine squared t equals 1 will be an important one. So find a vector function that defines the circle x plus 2 squared plus y minus 5 squared equals 9. So we're in 2 dimensions here. So first thing, getting this equation equal to 1 will be helpful. So we'll divide each piece by 9. And I want to rewrite it so this whole term is squared. So x plus 2 over 3 squared plus y minus 5 over 3 squared equals 1. So if we're trying to match it up to the Pythagorean identity, that means the x plus 2 over 3 has to be equivalent to cosine t, and the y minus 5 over 3 has to be equivalent to sine t. So x plus 2 over 3 equals cosine t, means x equals 3 cosine t minus 2, and y minus 5 over 3 equals sine t, y equals 3 sine t plus 5, right? And there we have our parameterization. Now here they don't specify a direction of travel, so we're good with this definition. If they did, it would just be something that we have to pay attention to, and we might have to adjust our parameterization, our vector function, accordingly, right? So r of t is 3 cos t minus 2, 3 sine t plus 5. Now, stepping this strategy into 3 space, find a vector function that represents the curve of intersection of the plane y plus z equals 1 and elliptic cylinder x squared plus y squared equals 4. Okay, so the cylinder, the elliptic cylinder in particular, is going to force us to use the Pythagorean identity in order to parameterize, right? So without solving for 1, let's try to be more direct here. X would be 2 cosine t, y would be 2 sine t, and now that we have x and y defined, we can go into the equation of the plane here, the same one from the previous slide. We can say z is equal to 1 minus y, which in this case means 1 minus 2 sine t. And r of t equals 2 cosine t, 2 sine t, 1 minus 2 sine t. So we talked about the direction of travel. The other piece here is if we only wanted to define those set of points once, we might include a domain restriction, let's say 0 to 2 pi on t. Right? If we didn't, if it needed to continue, we can eliminate that domain restriction. And the last strategy is we can solve the equations for the intersecting surfaces simultaneously, giving a curve whose equation we can parameterize. So essentially, what this means is we want to try to eliminate one variable, so then we get an equation in just, let's say, x and y. try to parameterize that equation, and then once you've parameterized x and y, you can then create a parameterization for z and create your vector function. So find a vector function that represents the curve of intersection of x equals 3z plus y minus 5 and x equals z plus 2y. So both of these surfaces are equal to x, so we could say that 3z plus y minus 5 equals z plus 2y, which says 2z minus 5 equals y. So now we have an equation with just a y and a z. In this case, y is defined in terms of z, so we'll build out from z. So z is equal to t, which makes y equal to 2t minus 5. And then we use one of the two original surfaces to define x. So let's go with z plus 2y. So z plus 2 times y. So that's x equals 5t minus 10. So our vector function is 5t minus 10, 2t minus 5t. Okay, so that finishes our discussion on vector functions. We talked about the algebraic components, domain, limits, and how all of that is just an extension of single variable functions and single variable calculus. We talked about graphing space curves, which is similar to graphing parametric equations. And then we created our own vector functions, which will be an important skill as we continue on in this course. So practice with these, get comfortable with these, and I'll see you at the next video.